In the bustling corridors of Springport High School, one educator stands out not only for his diverse knowledge of science but also for his deep commitment to fostering relationships with his students. Kyle Hutchinson, who teaches a variety of science classes including biology, chemistry, and forensics, embodies a modern approach to education that values personal connections as much as academic rigor. At just 31 years old, Hutchinson has already made a significant impact at Springport, having previously taught at Fowlerville Community Schools for 5 years before pursuing his passion in a smaller, more close-knit community. Hutchinson's journey into education was not a straight path. Growing up in Lansing, Michigan, he initially envisioned a career in architecture, but his love for science and the influence of his older sister, a music teacher, redirected him toward the classroom. Reflecting on his decision, he shared, "It's something that I've kind of always considered, which became clearer during his high school years. When I was applying for colleges, I asked friends and family what they could see me doing, and almost every single person said I could be a teacher. I think that just confirmed it for me." For Hutchinson, teaching is not just about imparting knowledge, it's about building a community where mutual respect thrives. He believes that strong relationships with students are crucial to their success. That's kind of a key component of student success in the classroom, having that strong relationship and mutual respect for each other, he noted. His approach has evolved over the years, transitioning from a more lenient style to one that emphasizes structure and accountability. A shift he credits to his experiences teaching 8th graders. One of the most rewarding moments of Hutchinson's teaching career came from a meaningful connection he forged with a student during his time at Fowlerville. He said, "I helped change his life around. He wasn't heading down a good path," Hutchinson recalled, recounting how he drew a bird as a mascot from a band they both liked in the student's graduation card. Years later, he received a message from the student, now successful and grounded, showing him a tattoo of that very bird. This exchange reaffirmed Hutchinson's belief in the profound impact educators can have on their students' lives. In his daily routine, Hutchinson finds joy in the variety of challenges that each day brings. "Every day it's always something new. It's never really monotonous or tedious," he remarked. Though he acknowledged the less glamorous side of grading. Nevertheless, it is the interactions with students and the opportunity to inspire them in the realm of science that truly drives his passion. As Hutchinson continues to cultivate a nurturing environment in his classroom, he embodies the hope that education can be a transformative force, not just for individuals but for the broader community. His journey illustrates the importance of mentorship and connection in education, reminding us that the bonds formed in classrooms can have lasting effects on students' lives. Looking ahead, Hutchinson's ongoing commitment to fostering relationships and inspiring young minds promises to influence the next generation of learners, showcasing the vital role educators play in shaping both knowledge and character. As the landscape of education evolves, the significance of such personal connections in teaching remains as crucial as ever. Highlighting the need for educators who are not only knowledgeable but also deeply invested in the holistic development of their students. Moderna's recent advancements in vaccine technology have generated significant excitement within the scientific community, particularly regarding its new combination vaccine designed to protect against both influenza and COVID-19. The latest Phase 3 trial results for the mRNA 1083 vaccine suggest that it may elicit a robust immune response, potentially providing equal or even superior protection compared to existing standalone vaccines. However, the path to regulatory approval is complicated by a shifting political landscape. The trial involved approximately 8,000 participants split into two age groups, individuals aged 50 to 64 and those over 65. According to the published results in the Journal of the American Medical Association, participants who received the mRNA 1083 vaccine exhibited a humoral immune response, measured through antibody generation, that was at least as strong as that observed in those who received the separate vaccines. Notably, the immune response to flu strains was particularly promising, with mRNA 1083 participants displaying higher antibody levels than their counterparts. Despite these encouraging findings, the vaccine's future is clouded by recent changes in the U.S. vaccine approval process. Under the direction of Health Secretary Robert F. Kennedy Jr., the Department of Health and Human Services has mandated stricter approval protocols requiring all new vaccines to undergo placebo-controlled trials. This has raised concerns among experts who argue that such regulations could be unnecessary and unethical, especially for vaccines that can be directly compared to existing options. Dr. Greg Poland, a vaccine response expert at the Mayo Clinic, expressed skepticism about the widespread acceptance of a combination shot, highlighting the differing seasonal patterns of influenza and the year-round prevalence of COVID-19. He emphasized the need for robust data demonstrating the vaccine's effectiveness in preventing both infection and hospitalization, particularly in light of the FDA's recent requests for more direct measures of efficacy. Moderna has since pushed back its anticipated approval date to 2026 as it works to address the FDA's concerns. The political backdrop complicates matters further. Kennedy's history of skepticism regarding mRNA vaccines has raised alarms among some stakeholders. His assertions, which include unfounded claims about the safety of these vaccines, could potentially hinder public confidence and acceptance of the new vaccine should it receive approval. Amidst this uncertainty, the potential for mRNA 1083 to revolutionize flu vaccination practices remains significant. The technology could facilitate faster production processes compared to traditional methods, which often rely on chicken eggs or large bioreactors. A successful combination vaccine could also enhance vaccination rates by simplifying the immunization process for patients, thereby bolstering public health efforts. As the scientific community awaits further developments, the implications of Moderna's combination vaccine extend beyond mere health benefits. They underscore the urgent need for a stable and supportive regulatory environment that fosters innovation while ensuring public safety. The future of such groundbreaking vaccines may hinge not only on the data they generate but also on the broader political and public discourse surrounding vaccine technology. In conclusion, while Moderna's mRNA 1083 vaccine shows promising efficacy in trials, its road to approval is fraught with political challenges that could impact its potential to reshape the landscape of flu and COVID-19 vaccinations. The coming months will be crucial in determining whether this innovative approach can overcome regulatory hurdles and gain the trust of the public and health authorities alike. In a significant breakthrough for lung cancer treatment, an international clinical trial has revealed that a new oral medication, zongertinib, is showing remarkable potential in treating patients with a particularly challenging form of the disease. This trial, which involved cooperation between Chinese and American researchers, offers renewed hope for those suffering from HER2-mutated non-small cell lung cancer (NSCLC), a condition that has historically been difficult to manage and treat effectively. The findings of the trial were published in the prestigious New England Journal of Medicine on April 28, 2025. Coinciding with presentations at the American Association for Cancer Research annual meeting in Chicago. Unlike existing treatment options, which primarily include an intravenous antibody-drug conjugate ADC that poses a range of side effects such as nausea and fatigue, zongertinib aims to provide a safer, more effective alternative by specifically targeting the HER2 protein. This protein plays a critical role in cell signaling related to growth, and zongertinib's mechanism involves blocking the activity of the protein's tyrosine kinase, thus curbing tumor growth. The trial spanned 82 sites globally, with 188 NSCLC patients participating, predominantly from Asian populations. Among the researchers, Professor Wang Xian from the Chinese Academy of Medical Sciences Cancer Hospital emphasized the significance of zongertinib, stating it could establish a new benchmark for targeted therapy in HER2-mutant NSCLC. This marks a pivotal moment in the oncology field, particularly for patients who have been left with limited options and high risks associated with standard therapies. The implications of this research are profound, especially considering the increasing global burden of lung cancer, which remains one of the leading causes of cancer-related deaths. The emergence of zongertinib not only signals a potential shift in treatment protocols but also reflects a broader trend towards personalized medicine, where therapies are tailored to the genetic profiles of tumors. As the trial results circulate within the medical community, the anticipated approval of zongertinib by regulatory bodies could pave the way for its integration into treatment regimens, offering hope to countless patients who currently face grim prognosis. The excitement surrounding this development is palpable as oncologists and researchers alike look forward to the possibility of a new effective weapon in the fight against a particularly aggressive cancer. Looking ahead, the focus will likely shift to the comprehensive evaluation of zongertinib's long-term efficacy and safety alongside its integration into existing therapeutic frameworks. Patients and healthcare providers will remain vigilant as the outcomes of this trial could reshape treatment landscapes not just in lung cancer but potentially in other malignancies characterized by similar genetic mutations. The ongoing evolution in cancer therapy continues to highlight the critical need for innovative research and collaboration across borders, fostering an environment where hope can flourish amidst the challenges of cancer treatment. In recent years, the demand for advanced computing power has surged, propelled by the rapid advancements in artificial intelligence (AI). However, traditional electronic microchips are beginning to hit performance and manufacturing limits, creating a pressing need for innovative alternatives. Recent studies published in Nature suggest that photonic chips, devices that utilize light for information processing, might provide the breakthrough required to meet this demand. Researchers have successfully addressed several critical challenges in the field, signaling a significant step toward the practical implementation of these powerful chips. Photonic chips present a promising solution due to their ability to process information at much higher speeds and bandwidths than conventional electronic chips. By employing photons instead of electrons, photonic computing circumvents the issues of electrical resistance and heat loss that plague traditional electronics. This technology is particularly advantageous for AI applications, especially in tasks such as matrix multiplications, which are fundamental to machine learning algorithms. However, the adoption of photonic chips has been hindered by several hurdles. Historically, the performance of these chips has been assessed in isolation, but for them to be viable, integration with existing electronic systems is crucial. This integration poses challenges, including the conversion of light signals into electrical signals, which can introduce delays that negate some of the speed benefits of photonic technology. Moreover, the current photonic systems are primarily based on analog operations, which can limit precision and restrict the types of tasks they can perform. Scaling up from small prototypes has also proven difficult due to fabrication challenges. The two recent studies have made significant strides in overcoming these obstacles. One team led by Bo Ping from the Singapore-based company Lightelligence introduced a new processor for photonic computing known as the Photonic Arithmetic Computing Engine PACE. This innovative processor features over 16,000 photonic components and is capable of executing complex computing tasks with minimal latency, demonstrating its feasibility for real-world applications. Ping noted this development represents a significant progression toward integrating photonic and electronic hardware, addressing accuracy and paving the way for scalable technology. In a separate paper, Nicholas Harris from Lightmatter and his colleagues showcased a photonic processor that can run AI systems with performance levels comparable to traditional electronic processors. Their experiments included generating text in the style of Shakespeare, accurately classifying movie reviews, and even playing classic Atari games like Pac-Man. Harris expressed optimism about the potential of photonic systems, stating, "Our findings indicate that photonic technology could support the next generation of hardware for AI applications." Both studies underscore that while photonic computing is not yet fully realized, it has the potential to revolutionize the AI landscape. The researchers believe that with further refinements, including the development of more effective materials and designs, photonic chips could play a vital role in the future of computing. As the tech community looks ahead, the advancements in photonic computing signify a pivotal moment in the ongoing quest for increased computational power. With the integration of these systems into mainstream technology, we could witness a new era of AI capabilities characterized by unprecedented speed and efficiency. The path forward involves collaboration between researchers and industry leaders to refine these technologies and address the remaining challenges, pointing to a future where photonic computing could reshape the landscape of artificial intelligence. In a promising development for the future of nuclear fusion, researchers at the Lawrence Livermore National Laboratory (LLNL) have made a groundbreaking discovery that could dramatically enhance the efficiency and lifespan of fusion reactors. This revelation, termed backflow saturation, may fundamentally change how scientists approach plasma technologies, with implications that extend far beyond the realm of energy production. The novel phenomenon was identified during investigations into the behavior of electrons in plasma, a state of matter essential for nuclear fusion. Traditionally, scientists believed that the flow of emitted electrons was primarily limited by the space charge effect, which is akin to a traffic jam caused by the mutual repulsion of electrons. However, the LLNL team has uncovered that backflow saturation, where previously emitted electrons reverse direction and flow back to the cathode, may actually impose a more significant restriction on electron flow. Backflow saturation happens when electrons previously emitted into the plasma reverse course and flow back toward the cathode, but it doesn't just limit electron flow, it also changes the plasma's state and its interactions with electrodes, the researchers noted. This insight could be pivotal for nuclear fusion technologies, particularly in tokamak reactors, which rely on precise control of superheated plasma. By strategically utilizing backflow saturation, researchers believe they can mitigate erosion of cathode surfaces in fusion reactors. This would reduce the energy of ions impacting these surfaces, thereby significantly decreasing material degradation due to sputtering. The potential outcome is a marked increase in the efficiency and longevity of plasma-based technologies, making fusion energy more viable as a sustainable energy source. To explore this phenomenon further, LLNL scientists developed an advanced simulation code that models the entire plasma diode system with unprecedented clarity. The simulations here were designed to advance theoretical understanding of current flow through plasmas, thus constraining parameters such as the mean density and collisional mean-free paths, said the research team. While these simulations provide compelling data, the team acknowledges the need for further experimental work to isolate and demonstrate the backflow saturation effect. The significance of this discovery extends beyond nuclear fusion reactors. Understanding electron flow from cathodes through plasmas is crucial for a wide array of plasma-based technologies, from plasma thrusters in spacecraft propulsion to industrial processing techniques. Understanding how many electrons can flow from cathodes through plasmas is a key problem in fundamental and applied physics, impacting the design efficiency and lifespan of various plasma-based technologies, the researchers concluded. In a parallel move toward harnessing nuclear fusion, the recent formation of the Great Lakes Fusion Energy Alliance at the Great Lakes Fusion Energy Summit underscores a growing commitment to advancing this field. This alliance, consisting of companies and stakeholders from the nuclear fusion sector, aims to facilitate collaboration and accelerate development efforts. Notably, the event highlighted the significant investments being made in fusion technologies, with the U.S. currently investing around $790 million annually, trailing only China's $1.5 billion. The summit featured discussions on the advantages of nuclear fusion as an energy source, emphasizing its potential to provide a steady, reliable power supply in contrast to the variability of solar and wind. With predictions suggesting that nuclear fusion plants could become operational by 2034 or 2035, the stakes are high. Advocates argue that while the initial costs of developing fusion facilities are daunting, the long-term benefits, particularly in terms of energy density and reduced environmental impact, make it a worthy investment. Moreover, grassroots initiatives are also emerging in the fusion landscape. A striking example is Hudhaifa Nazawardine, a student at the University of Waterloo who built a small fusion reactor in his bedroom for just $2,000. Though still a work in progress, his project exemplifies the growing accessibility of fusion technology to independent researchers. "This was by far the most annoying part of this project," he remarked, reflecting the challenges faced in achieving the high precision required for successful fusion. As efforts intensify toward realizing the promise of nuclear fusion, the recent breakthroughs in collaborative initiatives suggest a turning point in the pursuit of clean, sustainable energy. The convergence of scientific innovation, grassroots experimentation, and strategic partnerships paves the way for a future where fusion energy could play a crucial role in meeting global energy demands. As researchers continue to push the boundaries of what is possible, the dream of harnessing the same power that fuels the sun may finally be within reach. In a groundbreaking study published in ACS Publications, researchers have unveiled a novel synthesis method for rock salt-type nitrides that exhibit promising superconductive properties. This advancement not only enhances our understanding of superconductivity but also opens new avenues for future technological applications in electronics and energy transmission. The research focuses on zirconium-deficient nitrides, specifically the stoichiometric compound Zr1-hexan, where X indicates the level of zirconium deficiency. By utilizing a bulk synthesis technique, the team successfully created nitrogen-rich nitrides that demonstrate exceptional superconductive behavior. This work is particularly significant as it explores the relationship between the material's structure and its superconductive properties, a relationship that has been a subject of extensive research in materials science. Understanding the synthesis and properties of these nitrides is crucial for developing next-generation superconductors, said Dr. Emily Chen, the lead author of the study. Our findings suggest that manipulating the zirconium content can lead to enhanced superconductivity, which could have far-reaching implications for the field. Superconductivity, the phenomenon where materials exhibit zero electrical resistance under certain conditions, is vital for numerous applications including magnetic levitation, lossless energy transmission, and advanced computing. The discovery of a new class of superconductors could potentially lead to innovations that make these technologies more efficient and accessible. The implications of this research extend beyond theoretical interest. With the global push toward sustainable energy solutions, superconductors signify a leap in efficiency for power grids and electronic devices. The ability to synthesize these nitrogen-rich nitrides in bulk could pave the way for their practical use in commercial applications, making this a pivotal moment in materials science. As researchers continue to explore the intricate relationship between composition and superconductivity, the focus will likely shift to optimizing these materials for real-world applications. Future studies may delve deeper into the mechanisms that underpin their superconductive properties, aiming to unlock even greater efficiencies and functionalities. In conclusion, the bulk synthesis of nitrogen-rich zirconium-deficient nitrides marks a significant milestone in superconductivity research. As the scientific community builds on these findings, the potential for groundbreaking applications in energy and technology appears promising, heralding a new era in materials engineering that could transform our everyday lives.